I wanted to explore a concept I put forth at the end of our last video, where we said mechanical advantage exists even if there's no movement and no work. And we kind of proved it, but I wanted to do an actual math example. So let's draw ourselves out another example. And this time let's draw a different type of machine. Let's draw ourselves a lever. So that's just a rigid bar with some sort of turning point. And so we'll draw our turning point or our fulcrum, and we'll draw it a little bit closer to the left than it is to the right. And let's say we have some person balancing it out over here. So here's his leg. He's pushing down with some force, and give him some arms and a head. And he's pushing down on this lever with some force, balancing out the other side. And let's actually make this balance. So let's put some weight on the other side. So let's just draw a box, and let's say it weighs 50 pounds. And this 50-pound box is pushing down, and we'll call that the force resistance. Whereas the force that this person is pushing down with, we'll call that just our force effort. That's the effort that he's putting down. And we drew the fulcrum a little bit closer. Let's go ahead and clear up what those distances are. Let's keep these distances super simple. Let's say that this 50-pound weight is just 1 foot away from the fulcrum. And then let's say that this force effort, this where he's pushing down, where his leg is, let's say that that's 4 feet away from this turning point, otherwise known as this fulcrum. And so I want to be clear here. This system is completely balanced out. He's pushing down with just enough force to keep this side from going down, but he's not pushing enough to push it down, raising this side up. So let's write that out. Let's say there is absolutely no movement in this system. So the force effort is not traveling any distance, and the force resistant is not traveling any distance. That means we can say that our distance effort, our distance traveled by our force effort, equals 0. And we can say our distance resistance, or our distance traveled by our force resistance, also equals 0. And of course, this means that our work has to equal 0. And we know that's true because work equals force times distance. And it doesn't really matter how big our force is or what the force is. If the distance is 0, which we're saying it is, there is no movement, then the work has to be 0. And so there's no movement, there's no work. But if we look, we can see there is torque. There is a force on each side trying to cause this lever to rotate one way or the other. And they both have a radial distance. And a force causing a rotation with a radial distance is the definition of torque. And so both of these forces are trying to rotate this lever. This 50-pound weight is trying to rotate it counterclockwise, whereas this force effort is trying to cause it to rotate clockwise, but they're balancing each other out. And this is known as rotational equilibrium. And we've talked about rotational equilibrium before, but let's go ahead and define it. We hit on it a little bit in an earlier video, but we haven't actually taken the time to define it. So rotational equilibrium is where all the torques in a system, and torques is also known as moments. So we'll go ahead and write that out. So AKA moments. So all torques or all moments combine to cancel out so that there's no rotation. So the force on the left, this 50-pound weight, is applying some torque to our lever, and the force on the right is applying some torque on the lever, and neither one of them is actually rotating the lever, then we know they are in rotational equilibrium, so we can say that our torque at our resistance, so I'm just going to call that torque resistance for simplicity's sake, is equal to our torque at our force effort, and I'm just going to call that our torque effort, again, just to keep it simple. So we have torque, but we don't have work and we don't have movement. The question is there mechanical advantage? And there are two ways to calculate mechanical advantage. We can use our Imadeer equation, like we did over here in our inclined plane example. So we can say IMA equals dE over dr, but we already said those two numbers are 0. So, I mean, we have distances, but they're radial distances. They're not exactly distances traveled. So I'm not sure that we can use those to calculate our IMA. So let's leave that alone. What about our AMA? So we've also got our AMA-free equation. So we have AMA equals FR over FE, and we know our FR is 50 pounds, but do we know our FE? And well, we don't. So we're not sure if we can use our AMA because we don't know what our FE equals. But can we solve for our FE? Because if we can find our FE, then we can find our AMA. Remember, the formula for torque is force times a radius, and we have a radial distance of 4 feet, and we have a force effort. So if we can just find what our torque is, then we can find what our effort force is. And we already know that our torque is equal to our other torque, and we have everything we need to solve for our torque resistance. Let's look at it. So torque resistance equals force times radius, and our force for our torque resistance is 50 pounds. And we'll multiply that by its radial distance, which is 1 foot. And so hopefully you don't need a calculator for this. It's just 50 times 1 is 50, and feet times pounds is just foot-pounds. And so because our torque effort is equal to our torque resistance, we can then say our torque effort is also equal to 50 foot-pounds. And we can set that equal to our force effort, which we don't know, our Fe, multiplied by our radial distance for our force effort and our torque effort, which is 4 feet. And then it's just a simple algebra equation to solve for our force effort. We'll just divide by 4 feet on both sides. And so feet cancel out on the left, and 4 feet completely cancel out over here, and we're left with 50 divided by 4. So we pull out our handy-dandy calculator to figure that out. What is 50 divided by 4? And you might be able to do this in your head, but just in case, let's use our calculator. And we get 12.5. So we'll say our effort force equals 12.5 pounds. And if we know our effort force, then we can solve for our AMA. Remember, the formula for AMA is FR divided by FE, and FE was the only thing we were missing. So we can even go ahead and write out that equation again. AMA equals FR over FE, or AMA free, for our silly way of memorizing it. And now we know both of these numbers. We know that our FR is just 50 pounds, and we know our FE is 12.5 pounds. And so maybe you can figure this out. You just look back and you recognize the pattern. Let's even pull out our calculator. We said 50 divided by 4 is 12.5. Well, then 50 divided by 12.5 is 4, logically thinking about it. But if you're not sure how I did that, just in case, we can go ahead and do it. We can say 50 divided by 12.5 in our calculator. And what do we get? We get 4. Our AMA then equals 4. And so hopefully these two examples have removed any doubt that the mechanical advantage gained from a machine is consistent, even if there is no work and no movement in the system.